we need to be careful about, because this is where you take the standard deviation for the population, which is that sigma, and then we divide it by the square root of n, where of course n will represent, whatever your sample size is going to be. So let's see if we can do an example on this before we do the non-normal population. You can kind of see in that graph. Obviously, we don't have a bell-shaped curve. Let's try and look at number 19 over here for our example. And again, I'll copy this over to our Google Sheets where we've been doing our classroom examples. Again, you guys should have access to that. And again, just so you know, if you click on those three little lines on the bottom left corner of your Google Sheets, it actually shows you all the different sheets that are in there. And I'm just going to the last one that we had done, which was from 7.4. And then I'll add our new sheet. Alrighty, so this example, as you can see, is talking about the gestation period. And of course, we had done that same example right over here in section 7.2, if you look at that bottom. So, just kind of repeating the same examples, just in new scenarios. So the length of human pregnancies is approximately normally distributed. And of course, we need to know that the population is normal before we can apply those rules, right? So they're telling you the mean for the length of human pregnancies is 266 days with the standard deviation of 16 days. So they're asking us, what is the probability a randomly selected pregnancy lasts less than 260 days? So this is actually from the previous chapter. So can you tell me how we calculate this? How does, or what is the probability that a randomly selected pregnancy will last less than 260 days? So remember, you're talking normal distribution, which is what we had talked about in chapter 7. I'm trying to see if I So how do we go about finding this probability? That a pregnancy will last less than 260 days. So remember, by default, whenever you try to find the probabilities using our standard normal distribution, remember it always gives you to the left of the value that we are looking for. I'm trying to find an example here that one can actually show you. You will see by default, the area is always going to be to the left, right, of the value you're looking at. So really, you don't have to do a whole lot here. So if we're talking about, a normal curve, and again, I'm just gonna do a rough sketch over here. With a mean, obviously, right in the center of 266 days. And then you're talking 260. Somewhere over here, right? It's obviously not one standard deviation below the mean, because one standard deviation should be 16 days, whereas 260 is only 6 days less than 266, right? So you're not an entire one standard deviation below. So you definitely cannot use the empirical rule here, which means we have to go the traditional route, right? We find the z-score, and then either in the table 5 of your appendix A, you look up the probability there, or we can use technology, which is what I'm going to do today. I'm not going to show you the z-score method because I think I've done that enough times, so hopefully you guys are able to do that on your own. But I'm going to show it to you with the built-in function lambda distribution. Our, our mean of 266 days, standard deviation of 16 days. And then over here, our x value is of course the number given to us, which is 260. So remember, for norm dot distribution, you start by using your x value first. That's the 260, our mean is 266, standard deviation 16, and then for that last argument, cumulative, is where we type true. You can see that's what we're going to get from using the formula, the built-in function. You should get something similar if you find the z-score and then use the table 5 to find your probability over here. So you can see we're saying there's about a 35.38% or 0.3538 if we round it to 4 decimal places, that a randomly selected pregnancy will last less than 260 days, right? Because that is where the area is going to be, Now they are saying, suppose a random sample of 20 pregnancies is obtained. Describe the sampling distribution of the sample mean length of human pregnancies. Okay, so what are we going to do here? They're giving us a random sample of 20 pregnancies, right? So that's going to be our little n, our sample size. Is that too small, Erin? Are you having trouble seeing the numbers? Okay. Because I think I might be able to. Okay, so they're asking us to find or describe the sampling distribution of the sample mean length of human pregnancies. This is what we talked about in section 8.1 last. So what do we need to do here, guys? We just talked about this before we looked at this example. Let me show it to you. So the sample distribution will have a mean as same as the population mean and standard deviation has that formula there. So based on that, what are we gonna have for this guy? Remember, the mean for the sampling distribution is going to be what? Yeah, same as the population mean. And then what is the standard deviation for the sampling distribution? Nope, it's not the same. It is going to be 16 divided by square root of n. We take the standard deviation for the population and then divide it by square root of n. Again, guys, you need to keep these formulas handy. Remember, you can have, I think, what did we do last time? A 5x8 note card if you wanted that. And then, of course, when you do the take-home final exam, keep those handy. Alrighty. So we've got a random sample of 20 pregnancies. We've got our sample, just sampling distributions, mean and standard deviation. So now part C is asking us, what is the probability that a random sample of 20 pregnancies will have a mean gestation period of 260 days or less? So now this is for the sampling distribution, right? So we're saying we have a random sample of 20 pregnancies. So what's the probability that that random sample will have a mean of, 260 days or less? So remember, this is where we get into these type of examples over here. So you can kind of see we have looked at this guy, which this is greater than symbol, but you can still kind of get the idea of how we need to go about doing this. We're still talking about less, so we don't really have to use the complement rule or anything like that. So same process as we did before. We will use the norm dot distribution function for this, so we will do in this case, our X value is still 260 because they're still saying 260 or less. Remember, the mean and standard deviation will be the new ones that we calculated. So look how that probability changed from when we did part A, where you had a 0.3538, and this time you've got 0.046766, right? Because your standard deviation changed. It went from 16 to about 3.57 7. So, standard deviation changes, of course, your calculation will change. Now, remember when we're talking about interpreting these results, this is kind of what you're looking at, in the same kind of language as over here. So basically, we're saying if we take 100 random samples that have a size of 20, right? For the mean gestation period, we would basically say that about 4 of the samples will have a mean gestation period of, what was it, 260 or less days. So from 100 simple random samples. 100 simple random samples of well, if we had to round it up, we would say about 5 of them would have mean gestation period of 260 days. Because remember, now we're not talking about one single random sample, right? One single human person is not what we're talking about. We're saying if we picked hundreds of these random samples where there were 20 people in each random sample, out of those 100 samples, 5 of the samples might have a gestation period of 260 or less. Okay, so now for that was one part. See, I think I kind of messed up my parts. Maybe we'll see, but that's okay. Part B is saying what is the probability that that a random sample of 50 pregnancies has a mean gestation period of 260 days or less. So what do we need to modify here when they're saying in part B that our mean random sample is now 50 instead of 60? How will our math change here, guys? That's fine, it's not that hard. What needs to change so that we can change that random sample from 20 to 50? Well, yes, the end, but how will the math change? Standard deviation would change, right? Because standard deviation is where we do the square root of n being divided into the standard deviation. So of course, we know the mean will stay the same as the populations. Obviously, that is not going to change, but for the standard deviation, we're going to take 16 divided by now the square root of 50 because our sample size changed. So you can see how that standard deviation now is even smaller. So when we do the math for, and are they still keeping the days at 260 or less? They are. So now when we do the norm dot distribution, what will happen to the percentage? So we are looking at 260 as our X value. Mean is 266, standard deviation is this new one. And then of course we're cumulative, say true. So look what's happening as your standard deviation is getting smaller, your probability is also getting smaller, right? So now for this guy, what do you think this interpretation will change? So if you did 100 of these random samples of 50, how many of them will have a mean gestation period of 260 or less? What does that 0.004004997 become? 0.4. So you either do 0.4 or you increase your sample to 1,000, and we can say from 1,000, only 4 of them will have a mean gestation period of 216. Or less. If they wanted you to keep 100, then it would be 0.4. Okay, so just kind of remember that. I know your textbook, I think mostly kept it at 100, but I don't think they dealt with that many smaller values either, so I'm gonna keep it at 1,000. What might you conclude if a random sample of 50 pregnancies resulted in a mean gestation period of 260 or less? So that's actually this guy. What is the probability that a random sample of size 15 will have a mean gestation period within 10 days of the mean? So I want you to think about this. We're talking about a random sample of size 15. So of course we've changed that. And then what do we mean by within 10 days of the mean? Of course, we need to calculate the mean and standard deviation again, which of course. This can change. Standard deviation. Within 10 days of the mean. What are we looking at here, guys? What are our X values going to be? Mean is at 266. They're telling you what's the probability if we took a random sample size of 15 that the gestation period would be within 10 days. Are we doing above or below or both? Yeah, exactly, because when they say within 10 days, you're doing both ends. So I'm gonna call it X1 and X2, so the lower limit would be, of course, 10 days below. And then the upper limit would be 10 days above. So basically, you will need to find the probability for each of those X values. And then remember, this is where we take the difference between the two probabilities. So we'll do norm distribution for X1. And then we'll do distribution for X2. All right, so let's see what those two probabilities will come out to be. So let's start with the lower number, 256. We have a mean of 266, and then the standard deviation change. So we've got that first probability. Now for the second one. Alrighty, so now to find that probability. So again, remember the question was, what is the probability that a random sample of size 15 will have a mean gestation period basically from 256 days to 276 days? And you can see that's a fairly high probability. So as an interpretation, you would say, okay, so if we have a random sample of 15 people, 100 random samples, how many of them would fall under that category? So what does that 0.98? Yeah, So out of 100 random samples of 15 people each, 98 of them would have a mean gestation period within 10 days of the mean. Pretty high. So as you can see, guys, the math really is not different. It's how you calculate the mean and standard deviation, which again, the mean really is the same as the population mean, so you're not really calculating there. It's only as your sample size changes, you will need to calculate your new standard deviation and then use that to come up with your normal distribution values. Did any of you have questions on number 19? Alrighty, so that was using the normal population. So what happens if you are looking at non-normal? So as you can see, in this example here, we're saying, okay, the table 1 data represents the probability distribution of the number of people living in households in the United States. The figure, of course, is showing us the graph for that probability distribution. From the table 1, we determined that the mean is going to be 2.9, so approximately 2.9 people living in a household, and a standard deviation of 1.48. And of course, as you can see from that graph, it's obviously not a bell-shaped curve, so we know this probability distribution is not normal. They are also telling us that we actually have a discrete random variable here, because you can see how those lines are not connecting, or it's not a continuous flow, right? Like a bell curve is. So these numbers are discrete. So they're saying, okay, we can approximate our sampling distribution for the sample mean by obtaining 1,000 samples of size 4, size 10, size 30 from the population. And of course, they're talking about using technology here, right? So using simulation to do 1,000 samples of different population or sample sizes. And based on that, you can kind of see, I think they started out with size 4, it looks like, and went from there, and then they would repeat it for size 10 and size 30. So columns 1 and 2 represent the probability distribution, so you can see what those probabilities look like. They are also telling us each row in column 3 through 6, so those would be these last. So you can see it will be from column 3 to column 6. So these 4 columns over here, we're talking about how they list the number of individuals in each of those samples that they did, right? So you can see there were 4 people in one household, 1 person in one household, 4, 5, 7, 2, 4, 3, 2, 2, and you can kind of see all those different number of people in the households. Column 7 is where we are doing the mean, right? So you can see that's giving us the mean for each of those rows that we have. So the first row, there are 4 individuals in the first house, 2 in the second, 2 in the third, and 2 in the fourth. So you can see that mean is coming out to be 2.50. And then, you know, of course, you keep going horizontally. So now you've got 1, 3, 4, and 2. That also came out to be 2.5. We've got 4, 4, 2, 4 in that third row, and you've got 3.50, so on and so forth. So basically, you can see, okay, we had a sample size of 4. We did 1,000 samples of those. Our distribution is skewed to the right, as we saw from the graph. And then they're talking about when you did the mean of the 1,000 samples, it actually came out to be 2.9, and the standard deviation came out to be 0.76. So we're saying, okay, so the mean of the 1,000 sample equals the mean of the population, which again, so you can see the mean of the population was also 2.9, but the standard deviation was different. It was 1.48. So obviously we got the same mean for the 1,000 samples, but a different standard deviation of 0.76. So in this case also, you will see the mean for your sampling distribution equals the population mean. The standard deviation also technically follows that same formula that we just saw for normal distribution, which is the population standard deviation divided by the square root of n, which came out to be approximately 0.74. And you can see from the table, we got 0.76, so still pretty close to each other. And then, they're kind of doing with the population, sample size of 10, and then sample size of 30, and those are given to us in these two figures over here. So they have increased the sample size to 10 in this one. They've increased the sample size to 30 in this one, and this original is the one where they just had 4 as the sample size. So what are we noticing as we get to graph C? Isn't it looking more bell-shapy? That's a word. Right? So what's happening as we increase our sample size, you will see in sample size 4, we still had a little bit of a skewness to the right. As we got to sample size 10, the skewness is still there, but it's starting to take shape of that bell-shaped curve. But then as we got to sample size 30, you can see that's a pretty well-defined bell-shaped curve, and we're not seeing as much skewness to the right. So they're telling you here for a non-normal population that your mean of the sampling distribution of the sample mean will be the same as your population that you're getting the samples from. And your standard deviation will basically follow that same formula for the normal population, which is sigma divided by square root of n. And then they're also telling you in the second concept here is that the shape of the distribution of your sample mean will become approximately normal as your sample size n increases. And this does not matter what the shape of your underlying population was, because remember, our underlying population was skewed to the right. But in this case, as you increase your sample size, we start seeing that it's going to take that approximately normal shape here. So this is kind of where we get into the central limit theorem. This is where we talk, regardless of what the shape of the underlying population is, your sampling distribution of the sample means will become approximately normal as your sample size increases. Now, but normally, we always kind of use the general rule that you should have a sample size of 30 or larger for this to happen. Usually, if your sample size is smaller than 30, then you may not see that approximately normal curve. But I'm trying to see if that mentions it here, and I'm not seeing that being mentioned here. I would definitely ask you guys to go through these little paragraphs over here to just kind of get a sense of just what they're describing in detail. Now, they do kind of mention here, for example, the right skew distribution in example 4 required a sample size of about 30 before we start seeing that approximately normal shape. For uniform distribution, they're talking about the x value being between 0 and 10, including that. But they're not specifically saying 30 is kind of like our, rule of thumb kind of thing. So even for n equals 25, they are saying that you can have approximately normal shape, and that's this D graph over here. So they are kind of showing you with different sample sizes. So you can see this is from the population itself, and this one is talking about household income. This is when you did a sample size of 4. We can still see it's keeping that skewness to the right. As you did sample size of 10, it's getting better, but there's still the skewness to the right. And when we get to sample size of 25, we're starting to see the bell-shaped curve kind of happening. So yeah, this is what I was looking for. So you can see in that little box there, we're saying if the distribution of the population is unknown or it's not normal, then the distribution of your sample mean will be approximately normal, provided that your sample size is greater than or equal to 30. So this is kind of what I was talking about. So we use 30 as sort of like our cutoff number. So greater than or equal to 30, and then we can say, we can apply those same properties like we do for approximately normal sampling distribution here. All right, guys, so just another example here, we're talking about the mean weight gain during pregnancy is 30 pounds with a standard deviation of 12.9 pounds. Now weight gain during pregnancy is skewed, right? So you can see this is not a normal population. An obstetrician obtains a random sample of 35 low-income patients and determines their mean weight gain during pregnancy to be 36.2 pounds. So does this result suggest anything unusual? So then, of course, we're trying to understand what's the likelihood of obtaining a sample mean of 36 pounds or maybe even higher. Because, you know, we're talking about unusual weight gain over here. So you can see we're kind of doing the same math here. Your mean for the sampling distribution will be the same as the population mean, which was 30. To calculate the standard deviation, we take the population standard deviation and divide it by square root of n. So you can see that math over there. So here we're saying it seems reasonable that there are at least 700 low-income pregnant women in the population. So the sample size is less than 5% of the population because we're only using 35 as our sample size. The probability for our mean, sample mean being greater than or equal to 36.2, you can kind of see they're going through the Z-score calculation, which comes out to be a value of 2.84. Put that in your table and come up with the probability. But remember, we're talking about 36.2 or greater, right? So we are looking at the area on the right-hand side. So you take the value you get from either the norm distribution function or from the table, and then subtract that from 1 to get that area. And you can see that area comes out to be 0.0023 on using technology, comes out to be 0.0022. So that's a fairly small probability. So we're saying if the population from which the sample has been drawn had a mean weight of 30, pounds that you're gaining on pregnancy, a probability that the random sample of 35 women will have a sample mean weight gain of 36.2 is approximately, again, you can see how small that number is, 0.002. So you can see that means from the 1,000 samples we collect of 35 pregnant women who gain weight, 2 from those 1,000 samples would have a mean of 36.2 or higher. So yeah, this is very small. So you can kind of see the conclusions that are coming out on this. We're saying the mean weight gain of low-income patients is 30 pounds, and we happen to select women who on average gain more weight. The mean weight gain for low-income patients is more than 30 pounds. So we are inclined to accept the second explanation over the first, since our sample was obtained randomly. So the obstetrician should be concerned. Perhaps you should look at the diets and lifestyles while they are pregnant, because we're talking about weight gain during pregnancy. Yeah, that question was the mean weight gain being 36.2. Does this result suggest anything unusual? And we are saying yes, this number is concerning. So maybe is it the lifestyle, is it the diet of the people not helping them keep a healthy weight, but they're gaining more weight than they should be. So basically, guys, you should see here that it does not matter if your original population is normal or not normal. If the original is normal, then of course, we go through the same calculation as you can see on the top row. But the bottom row is telling you if the population is not normal, then remember, this is where we have that 30 as our sample size cutoff, right? If you have a sample size of 30 or more, then we are able to follow that same mean and standard deviation calculation as before. But if your sample size is gonna be smaller than 30, then that's where the concerns would start. I mean, okay, so number 25 is telling us it's an unknown shape of the distribution, so we should be. This is number 25. With the shape of the distribution of the time required to get an oil change at a 10-minute oil change facility is unknown. However, records indicate that the mean time for oil change is 11.4 minutes. And let's see, standard deviation is 3.2. Okay. To compute probabilities regarding the sample mean using the normal model, what sample size would be required? So for us to use the normal model, what's our cutoff for the sample size? Yep, n has to be greater than or equal to 30. Okay. What is the probability that a random sample of n equals 40 oil changes results in a sample mean time of less than 10 minutes? Okay, so they're giving us n as 40, which is larger than 30, so we're good to go. We can use the normal model. So this is where you then need to calculate the mean and standard deviation. So they're telling us the mean sample time of less than 10 minutes. So your X value will be 10. Remember, the mean is the same as the population mean, so no calculation there, but standard deviation is where we need to calculate. So you take the population standard deviation and divide it by the square root of your sample size, which is 40. So that gives us our standard deviation. And now you can use the built-in function, right? Again, dot distribution. So our X value was 10 minutes or less, or actually less than 10 minutes. Our mean is 1.4, and then we just calculate our standard deviation. So you can see, since we have such a small number, we'll again jump to 1,000. So we would say for 1,000 simple random samples of n equals 40. What would that be? 3 out of 1,000. Okay, suppose the manager agrees to pay each employee a $50 bonus if they meet a certain goal. On a typical Saturday, the oil change facility will perform 40 oil changes between 10 a.m. and 12 p.m., treating this as a random sample, what mean oil change time would there be a 10% chance of being at or below? This will be the goal established by the manager. So read that again one more time. And how would we go about finding that out? They're asking us to find the mean, right? And they're giving us the percentage. So we should put N at 40 because they told us to use that as our random sample. We have to find the mean. You can both calculate the standard deviation because you have the standard deviation from the population, and then you do the square root of your sample size, which is 40. What does the 10% represent? That is actually what this answer comes out to be, right? When we plug in our X value, our mean, our standard deviation, it gives us the probability, right? So they're giving you the probability. They're saying there would be a 10% chance of being at or below the mean. So your probability is 10%, which you know as a decimal would be 0.1. So how do we go backwards to find the mean? Who's that? Yes, very good. We need to find the z-score. So you need to go to the table here actually and figure out what the table 5, and we're looking for 10%, so 0.1. Which should be in this negative side of the table, because we are talking about being below the mean, right, or maximum at 10% or below, so 0.10 is it's gotta be between these two numbers. Okay, there we go. So you can see right here, we've got 0.1003 and we've got 0.0985. So out of these two numbers, which one is closer to 0.10? Yeah, because that is only 3 units away, whereas the other one is 15 units away, if you think of that as being in 1,000. So the z-score you would be going with is going to be 2.1003, which looks like is going to be negative 1.2. This is third down, right? So third down is negative 1.2, and of course that column is 0.8. So our z-score is negative 1.28. Okay, so what do we do after we find the z-score? How do we find the mean? Z-score is defined as x minus the mean divided by the standard deviation. So to reverse that, right? So that means to find the mean, we would need to work backwards, so you would have to take your z-score. And since you're dividing by standard deviation, you of course end up multiplying by the standard deviation. And then what? We've got z-score, which is x minus b divided by the standard deviation, and this will be the standard distribution. So I'll just put a little x bar on it. So you're trying to get mean by itself, which means you take the z-score, multiply by the standard deviation, and that would leave you with x minus the mean on the other side, right? And then basically we need to subtract by x, but since you have a negative sign over here, we would basically need to multiply everything by negative, so that means you would actually end up multiplying here, so you would basically end up with mean equals z times standard deviation, and then add your x value to it. So we don't even have an x value. We came up with that z-score. What am I doing? So we've got our 40 oil changes. We've got what mean oil change time would there be a 10% chance. 10% chance. Okay. I think we can actually calculate that because we know. actually interesting. I didn't think it was going to. Probably because I confused myself with the mean. So the, remember the sample mean, sorry, the population mean is at 11.4. So for the sample, we are saying for 10% or less, the sample mean should be at 10.7515. Now I'm trying to see how do we calculate that with 11.4 as our population. So if we took 11.4 and subtract with 0.2, which is the z-score, we came here. That's one control the same population. That's one control. Slightly different calculation when I'm using technology to do this versus using the z-score. Now, remember the probability that we had used was 0.1003. So obviously with the table, you're not going to get a very precise answer, but you can see they're in the same neighborhood, but it is going to be a little bit different. So my bad, I thought we had to calculate the mean, which we don't. We're calculating the sample mean for our population of a sample size of 40 people, right? Between 10 to 12. But just like we did for part B, for the calculation, you're still using for the sampling distribution, you're still using the same mean as the population mean. So yeah, that mean needed to still stay at 11.4. Just the X value that we're calculating, the sample mean is going to be either of these two.
Let's say like for our homework, we do that, which answer would we put? Would we just have to try both and see which one?
So usually for problems like these, they give you a threshold. So they will tell you like they may give you like from 10.10 to 10.90. So usually they give you a pretty broad decimal approximation because they know that you could be using technology or you could be using the table. So based on that, your answers can come up. And sometimes even if they don't give you a range of numbers, they will give you 4 or 5 different options. So I don't know if you've noticed that with other probability distributions, a lot of times you may get like 10.100, but then when you click on the correct answer, it may say 10.100, 10.11, 10.12. So sometimes it gives you like 3 or 4 different correct answer options because it depends on which method you use to calculate. Because you know, from the table, you're never going to get a precise answer. You're always going to get an approximate, right? Which is that 10.12. But when you use technology, because we're not rounding numbers, we're not doing anything, it gives you a little bit more of an accurate answer than what we would get from the table. So I would say try, and if it's constantly saying it's wrong, let me know and I can go in and see what's going on, why it's not accepting my answer. But it should accept, in our case, either of those two answers. All right, very good. Any other questions on this? And I'll clean this up before I put it to, you know, it has a little bit more semblance of an order here than what I have. All right, so 8.2 here kind of is talking about the same thing, but we're getting into excuse me, discussions about a sample proportion. So remember, we talked about sample means in section 8.1. Here, we're talking about a sample proportion. So just as an example here, you can see they're saying, suppose we want to determine the proportion of households in a 1,000 house homeowners association. So there are 100, you know, members, or however you want to look at that, that favor an increase in the annual assessments to pay for neighborhood improvements. So we could survey all the households to learn which ones are in favor of those higher assessments. If 65 of the 100 households favor that higher assessment, the population proportion P of households would, then come out to be, of course, 65 out of 100, right? They're saying, yeah, we're in favor of these higher assessments. But gaining access to all individuals in that population would be rare. So this is where, again, we kind of think about estimating the parameters instead of, going to every 100 household and asking them, hey, what's your opinion on this? So here we're saying, okay, suppose you have a random sample of size n from your population, in which each individual either does or does not have a certain characteristic. So the sample proportion, and since we're talking in terms of a sample proportion here, to differentiate it from that population proportion of P that we looked at over here, we call this P hat. You can see we're putting a little caret symbol on top of the P. So that way we know we're talking about the sample proportion here. And in this case, you will see it's going to be X divided by N, where X will represent, whatever that characteristic we're looking for, which could be households that are in favor of the higher assessment. And then, of course, N would represent your sample size, so you divide by N. And they're kind of referencing here that if you look at the section 6.2 where we talked about binomial probabilities, X can also be thought as number of successes, right? Which have that characteristics, whereas failure, which do not have that characteristic. So that's kind of a neat way of thinking about that also. So as an example, you can see here the Harris poll conducted a survey of 1,200 adult Americans who vacation during the summer and asked whether the individuals plan to work while on summer vacation. So of the surveyed, 552 indicated that they plan to work while on vacation. And they're again asking us to find the sample proportion here. So you can see again, very simple. 552 said yes, they plan to work during vacation. We had a total of 1,200 people in the survey, right? So that's your sample size. So you can see P hat is literally 552 divided by 1,200, which of course comes out to be 0.46. And that's going to be your estimated proportion here of 46% or 0.46 of people who plan to work on vacation. So again, if we did a second survey of, again, 1,200 Americans, we would probably end up having a little bit of a different estimate depending on how many people said they were going to work during vacation. Because the value of P hat varies from sample to sample, it is a random variable, and therefore it can have a probability distribution of its own. So again, they're saying to get a sense of the shape, the center, the spread, we could repeat the exercise of, where we keep getting those 1,200 random samples of Americans over and over again. And then, of course, we could build our sample proportion based on that. We could get a histogram, which would then tell us the shape. We could get a mean, we could get a standard deviation. Pretty much everything that we did in section 8.1, but instead of working with sample means, here we're talking about sample proportion, which is that P hat calculation of X divided by N. So what would that look like in a probability distribution here? So you can see, again, we're talking about, based on a study by Gallup, 76% of Americans believe that state of moral values in the US is getting worse. And you can see the different sample sizes. They're asking us to do this with 10, 25, and 60. They just kind of go through the description of how they approach that, which again, like I said, will be very similar to what we were doing in section. But let's take a look at what this looks like. So you can see you've got your rows with all the samples in it. So you know how many people believe that the morals are, kind of going worse. You've got your P hat at the end in that last column of 0.7, 0.7, 0.8, 0.8, so on and so forth. So now we've got our proportions here. So you can see with sample size 10, we've kind of got a little bit of a left skew going, right? With the sample size of 25, it's getting more bell-shapy, but there's still a left skew. But look at with that sample size of 60, it's looking more, more symmetrical, more bell-shaped. then it is looking left skewed. So here again, you can see as the size of your sample increases, the shape starts becoming approximately normal. The mean of your sample proportion will again be equal to what it was for the population proportion. And then the standard deviation of the distribution will actually decrease as the sample size increases. And again, these were the same observations we made in section 8.1 when we were talking about them. So you will see we're still using that same calculation here of n times p times 1 minus p. If that product comes out to be greater than or equal to 10, we can say that sampling distribution is going to be approximately normal. Your mean for the sampling distribution is the same as your population proportion. So that's the p-value here, guys, not mu. For the population, and then you can see the calculation for calculating the standard deviation for your population. Sorry, sampling distribution. So obviously the math changes a little bit because you're looking at proportions here as opposed to means. Okay, so we'll pick up from here and we'll talk about how to do these calculations, do a couple examples, and then we'll move on to hypothesis testing and confidence intervals, okay? So I will change the homework due date for chapter 8 to next Monday. And then I'll probably put the deadline in for chapters 9 and 10 also, so that you guys at least have an idea of when to finish this. Okay, if any questions pop up, please let me know. And I will see you guys on Wednesday. Have a great Monday, guys. Take care.